Imagine a star so dense that a teaspoon of its material would weigh as much as Mount Everest. Now imagine that star spinning 700 times per second, its surface moving at nearly 1/4 the speed of light. Its magnetic field is 1,000,000,000,000 times stronger than Earth's, powerful enough to erase your credit cards from halfway across the solar system. These objects exist. We call them magnetars. But here's what you don't know. Some of them aren't dead at all. They're feeding, growing stronger, defying the fundamental laws that govern stellar death. In 2004, astronomers detected something impossible, a burst of energy so powerful it briefly outshone the entire galaxy. The source? A magnetar suddenly awakening after decades of silence, its surface cracking like broken glass as it consumed material from a companion star it had slowly devoured over millennia. What if the most dangerous objects in the universe aren't black holes? What if something far stranger lurks in the darkness between stars, waiting to feed? Today, we journey through evidence that challenges everything we thought we knew about stellar death, cosmic magnetism, and the violent transformation of matter at the edge of physical law. Prepare yourselves. We begin. December 27th, 2004. NASA's Swift satellite detected something that should have been impossible. A wave of gamma rays struck Earth's atmosphere with such intensity that it ionized the upper layers, disrupting radio communications across the entire Pacific Ocean. The burst lasted just 1/10 of a second, but in that fraction of time, it released more energy than our sun produces in 150,000 years. The source was SGR 180620, an object 50,000 light-years away on the far side of our galaxy. Astronomers had been monitoring it for years, cataloging it as a soft gamma repeater, a strange class of neutron star that occasionally hiccups bursts of radiation. But this was no hiccup. This was a cataclysm. Dr. Kevin Hurley at the University of California, Berkeley, led the team analyzing the data. What they discovered rewrote the textbooks. The object wasn't just a neutron star, it was a magnetar, a stellar corpse with a magnetic field so powerful it warps the quantum vacuum itself. To understand magnetars, we must first understand neutron stars. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity's relentless pull. The core collapses in less than a second, crushing matter to densities that shouldn't exist outside black holes. Protons and electrons merge into neutrons, creating an object the mass of the sun compressed into a sphere just 20 kilometers across. Picture this. If you could bring a grain of sand from a neutron star to Earth, it would weigh 100,000 tons, more than the largest aircraft carrier. The entire star contains more mass than our sun, yet you could drive across its diameter in 15 minutes at highway speeds. But magnetars take this impossibility further. During the collapse that creates them, magnetic field lines get compressed and amplified beyond comprehension. The resulting magnetic field reaches strengths of 100 trillion Gauss, a quadrillion times stronger than Earth's magnetic field. At these intensities, magnetism stops being just a force. It becomes a fundamental property of space-time itself. The magnetic field is so intense, it creates something called magnetic pressure. The field literally pushes against the star's surface with forces equivalent to billions of atmospheres, cracking the neutron star's crystalline crust like eggshell. When these cracks occur, they release starquakes, seismic events that make Earth's strongest earthquakes look like gentle vibrations.
For decades, scientists believed magnetars were solitary objects, cosmic lighthouses spinning alone in the darkness, gradually losing energy over millions of years until they went silent forever. The mathematics seemed clear. A magnetar's powerful magnetic field should slow its rotation through a process called magnetic braking. Within 10,000 years, most should spin down to the point where their magnetic fields can no longer generate particle emissions. They should become dark, quiet, invisible. But observations kept contradicting this neat picture. In 2008, the Chandra X-ray Observatory detected something peculiar around several magnetars, faint, extended emissions that shouldn't exist around objects supposed to be magnetically isolated. The radiation patterns suggested the presence of material being heated to millions of degrees, but where was this material coming from? Then came the revelation that changed everything. Using the Very Large Array radio telescope in New Mexico, astronomers discovered that nearly 1/3 of known magnetars show evidence of binary companions, stars orbiting nearby, sometimes just barely outside the magnetar's gravitational grip. Dr. Vikram Dhillon at the University of Sheffield captured optical observations showing material streaming from these companion stars, pulled inexorably toward the magnetar like water circling a drain. But this wasn't ordinary accretion. The material wasn't forming a disk. Instead, the magnetar's trillion Gauss magnetic field was channeling it directly onto the magnetic poles, creating focused beams of X-ray emission. The implications were staggering. Magnetars weren't dying, some were feeding, and when they fed, they awakened. But this represents just one piece of a much larger puzzle hidden in the violent deaths of massive stars and the strange objects they leave behind.
The first concrete evidence came from an object classified as an ordinary pulsar, PSR J18460258. Sat in the supernova remnant KESS 75, spinning 3.1 times per second, slow by pulsar standards, but unremarkable. For years, it behaved exactly as predicted, a dead star's ember, predictably dimming. Then, on May 29, 2006, it exploded. Over just 4 hours, it emitted dozens of short bursts of gamma rays. Its X-ray luminosity increased by a factor of 100. The rotation rate didn't slow, it accelerated slightly, gaining energy from somewhere. Analysis revealed the truth. PSR J18460258 had been hiding its nature. Its magnetic field was 50 times stronger than initially measured, firmly in magnetar territory at 5 trillion Gauss. But more remarkably, observations showed faint wisps of material in a ring around the neutron star, the scattered remnants of a companion that had ventured too close centuries earlier. The magnetar had consumed its companion over decades or centuries, slowly accreting material that amplified its magnetic field and loaded the crust with stress. When the crust finally fractured in 2006, it released all that accumulated energy at once. This wasn't stellar death. This was stellar transformation, powered by cosmic cannibalism.
When astrophysicists model magnetar formation, they encounter a fundamental problem. Theoretical calculations suggest that magnetars should form from stars of very specific masses, between 10 and 25 times the mass of the Sun. Stars more massive than this should collapse directly into black holes. Stars less massive should produce ordinary neutron stars. But here's the puzzle. We find magnetars where they shouldn't exist. Some sit in supernova remnants from stars that were clearly too massive, 40 or even 50 solar masses based on the remnant chemistry. Others appear in regions where star formation suggests progenitor masses far too small. Dr. Norbert Langer at the University of Bonn proposed a solution that at first seemed radical: mass transfer before death. If a massive star has a companion, the two can exchange material throughout their lifetimes. A star born with 40 solar masses might shed most of its mass to a companion before collapse, leaving behind a core of exactly the right mass to form a magnetar rather than a black hole. The evidence supports this dramatically. Statistical surveys show that magnetars are 3 to 4 times more likely to exist in regions where binary star systems are common. In dense stellar clusters where stars form in pairs and triples, magnetar formation rates spike. The implication is profound. Magnetars may not be rare cosmic accidents. They may be the deliberate product of stellar vampirism, stars feeding on companions throughout their lives, then inheriting those companions' material after death to sustain themselves further.
Conventional physics says magnetars should spin down. Magnetic braking should inexorably slow their rotation as energy radiates away through electromagnetic waves. Every pulsar we observe follows this pattern. Their periods gradually lengthen over time, except when they don't. 1E1841-045, a magnetar in the constellation Aquila, has been monitored continuously since 1995. Its rotation period is 11.8 seconds, making it one of the slowest spinning magnetars known. Standard models predicted it should slow by about 0.00001 seconds per year. Instead, in 2011, astronomers detected something impossible. The magnetar began spinning faster. Over 3 months, its period decreased by several microseconds, a small change, but in the wrong direction entirely. The acceleration required an input of rotational energy equivalent to 10,000 times Earth's total annual energy consumption. Where did this energy come from? The only plausible source: accretion of material from an external source. Observations with the New Star telescope revealed periodic X-ray variations with an 18.5-day cycle, the telltale sign of a companion star orbiting the magnetar, shedding material with each close approach. The magnetar wasn't just accreting material, it was actively extracting angular momentum from its companion's orbit, like a cosmic turbine driven by stolen stellar wind. When the Chandra X-ray Observatory conducted a systematic survey of magnetars in 2012, researchers expected to see isolated point sources, bright spots in the X-ray sky with nothing around them. Instead, they found something peculiar: extended X-ray tails streaming from nearly 40% of magnetar sources. These tails stretch for light years, glowing at temperatures of several million degrees. Detailed spectroscopy reveals chemical signatures that shouldn't exist in interstellar space: highly ionized iron, silicon, and carbon in proportions that match stellar atmospheres, not supernova remnants. The smoking gun came from 4U0142+61, a magnetar 13,000 light-years away in Cassiopeia. Its X-ray tail extends 20 light-years and shows clear chemical stratification: lighter elements on the outside, heavier elements toward the center. This pattern precisely matches theoretical models of materials stripped from a companion star's atmosphere and ionized by the magnetar's intense radiation field. But here's where it gets strange. The amount of material in these tails far exceeds what could be stripped from a companion in the magnetar's lifetime. The mass in the tail of 4U0142+61 alone equals roughly 1/10 the mass of our Sun. No ordinary companion could provide this much material, unless The companion itself was massive, and the magnetar has been feeding for far longer than anyone suspected. This represents just one piece of a much larger puzzle hidden in the violent evolution of close binary systems. In recent years, astronomers have identified a new class of supernova explosions called ultra-stripped supernovae. These explosions are faint, 100 times dimmer than typical supernovae, and they expand unusually slowly. Their spectral signatures reveal something remarkable. The progenitor stars had lost almost all their outer layers before exploding, leaving behind only the dense iron core and a thin envelope. The first well-studied example, SN 2005 EK, released just 1/100th the energy of a normal supernova, yet models showed the progenitor had originally been a massive star, 20 to 25 solar masses. Somehow, it had been stripped down to just 2 to 3 solar masses of material before death. The only mechanism that can strip a star this thoroughly is mass transfer to a compact companion. Not just any companion, one with powerful magnetic fields that can tear material away through magnetic interaction rather than simple gravitational accretion. Dr. Selma de Mink at Harvard University ran computer simulations of binary systems where one star has already become a magnetar. The results were stunning. The magnetar's magnetic field extends far beyond its physical surface, creating a magnetosphere that reaches out millions of kilometers. When the companion star expands into a red giant phase, this magnetosphere doesn't just siphon material, it strips the star like a cosmic sandblaster, removing layer after layer until almost nothing remains. When the stripped companion finally explodes, it creates an ultra-stripped supernova. And the explosion often leaves behind another neutron star, now in a tight orbit with the original magnetar. The system becomes a binary magnetar pair, or in many cases, the second explosion provides so much material to the first magnetar that it triggers a transformation. When astronomers catalog magnetar rotation periods, they find a curious pattern. There are almost no magnetars with periods between 2 and 8 seconds. Faster than 2 seconds? Yes, plenty. Slower than 8 seconds? Absolutely. But that middle range appears nearly empty, a gap that shouldn't exist if magnetars form through simple stellar collapse. This period gap remained unexplained until Dr. Krissa Kuveliotou at NASA's Marshall Space Flight Center analyzed decades of observational data. Her team discovered something remarkable. Magnetars don't stay in the gap, they pass through it. Multiple magnetars have been observed with periods around 2 seconds that, over years of observation, slow down toward the gap, then suddenly accelerate, jumping past it to periods of 10 seconds or more. The transition happens over timescales of just months, far faster than magnetic braking alone could explain. The only mechanism that fits the observations: periodic accretion events. As the magnetar's companion star evolves, it goes through phases of stability and instability. During unstable phases, material falls onto the magnetar, spinning it up and increasing its magnetic field strength. During stable phases, the magnetar spins down through normal magnetic braking. The gap represents the unstable transition period. Magnetars don't linger there because the accretion physics are chaotic and short-lived. Even more remarkably, spectroscopic observations during these transitions show chemical signatures changing in real time. Before the transition, emissions show mostly hydrogen and helium. After the transition, they show enriched metals, evidence that the accreting material comes from progressively deeper layers of the companion star as it's stripped away. The magnetars are literally eating their companions from the outside in, layer by layer, and the consumption shows up in their spectral signatures like cosmic stomach contents. In 2019, astronomers detected something unprecedented: a nova-like outburst from a known magnetar candidate. The object, Swift J 1818.0-1607, suddenly brightened by a factor of 1,000 in visible light while simultaneously emitting intense X-ray flares. The outburst lasted 3 days, then faded. This behavior mirrors classical novae, thermonuclear explosions on the surfaces of white dwarfs accreting material from companions. But magnetars aren't white dwarfs. They're neutron stars with fundamentally different physics. The material falling onto a magnetar shouldn't accumulate. It should be channeled directly onto the magnetic poles and radiated away as X-rays. Unless something changes the rules. Dr. Thomas Macaron at Texas Tech University proposed a mechanism that seems impossible, yet fits the observations perfectly. If a magnetar accretes material rapidly enough, roughly 1/1,000,000th of a solar mass per year, the material doesn't have time to be channeled magnetically. Instead, it briefly accumulates on the surface, heating up through compression until it reaches temperatures where nuclear fusion ignites. The fusion doesn't produce a sustained burn like in a normal star. Instead, it detonates all at once, blasting excess material into space while simultaneously generating a burst of gamma rays as the explosion channels through the magnetar's magnetic field lines. The result looks exactly like what Swift J 1818.0-1607 displayed, a nova-bright optical flare combined with magnetar-typical high-energy emission. Since 2019, 3 additional magnetars have shown similar outbursts. All 3 have confirmed or suspected binary companions. The recurrence rate suggests these thermonuclear explosions happen every few decades, meaning magnetars in binary systems are regularly consuming and detonating their companions' material in violent cycles of stellar vampirism. Gamma-ray binaries are systems where 2 objects, typically a neutron star and a massive star, orbit so closely that their interaction generates persistent gamma-ray emission. Only about a dozen such systems are known in our entire galaxy, making them exceedingly rare. Here's the paradox. Of those dozen systems, at least 5 show magnetic field signatures consistent with magnetars rather than ordinary pulsars. The fraction is impossibly high. Magnetars make up perhaps 10% of all neutron stars, yet they dominate gamma-ray binaries. The statistical improbability of this caught the attention of Dr. Guillaume Dubas at the Grenoble Institute of Planetology and Astrophysics. His analysis revealed a stunning correlation. The gamma-ray binaries with magnetar signatures also show evidence of extreme mass transfer, companion stars losing material at rates 10 to 100 times higher than similar systems with ordinary pulsars. The implication is profound. Magnetars don't just passively accept material from companions. Their ultra-powerful magnetic fields actively strip material away, creating interaction zones where charged particles accelerate to nearly light speed before colliding with the companion's stellar wind. These collisions generate the gamma rays we observe. The magnetars aren't just feeding, they're actively hunting, using their magnetic fields as tools to extract maximum material from their stellar prey. The evidence extends beyond individual systems into the realm of galactic evolution itself. The accumulated evidence points to a coherent picture of magnetar evolution that challenges traditional stellar death theory. The story begins not with a solitary star, but with a binary system, 2 massive stars born together, orbiting in a cosmic dance that will last millions of years. As the more massive star evolves faster, it expands into a red supergiant, filling its Roche lobe, the gravitational boundary beyond which material gets pulled toward the companion. Mass transfer begins, but with a twist. The more massive star's core is already generating powerful magnetic fields through dynamo processes deep within. When it finally explodes as a supernova, these seed fields get amplified by collapse into the magnetar's trillion Gauss field. But the explosion doesn't destroy the binary. Computer simulations by Dr. Philip Podsiadlowski at Oxford University showed that if the supernova is asymmetric, and most are, the system can remain bound. The companion star, now orbiting a newly formed magnetar, continues its evolution. This is where stellar vampirism truly begins. The magnetar's magnetic field extends millions of kilometers into space, creating a magnetosphere that acts like a magnetic funnel. As the companion star evolves into a red giant, its outer atmosphere extends into this magnetosphere. Material doesn't fall directly onto the magnetar, it follows magnetic field lines, spiraling inward and accelerating to relativistic speeds. The process is self-reinforcing. Accretion adds angular momentum to the magnetar, spinning it faster. Faster rotation generates stronger magnetic fields through amplification of internal currents. Stronger magnetic fields strip material more efficiently. The cycle continues, with the magnetar growing more powerful as it devours its companion.
But here's the central mystery that kept theorists puzzled. Where do magnetar strength fields come from in the first place? Standard dynamo theory, the process that generates Earth's magnetic field or the Sun's, cannot produce fields stronger than about 100 billion Gauss. To reach the quadrillion Gauss fields of magnetars requires something more extreme. Dr. Sandro Meneghetti at the Institute for Space Astrophysics in Milan proposed what's now called the fossil field hypothesis. The idea, massive stars form with magnetic fields trapped in their cores during birth. As the star evolves, these fields remain locked in the core, potentially amplified by rotation and convection. When collapse occurs, these fields get compressed along with the matter, amplifying them by factors of 1 billion or more. But recent observations complicate this picture. Several magnetars show magnetic fields that are too strong, exceeding even optimistic fossil field predictions by factors of 10 or more. These ultramagnetars seem to have fields approaching the quantum electrodynamic limit, where the magnetic field energy density equals the mass energy density of the vacuum itself. At these strengths, virtual particle pairs spontaneously form from the vacuum, only to be ripped apart by the field before they can annihilate. The solution may lie in accretion itself. Dr. Konstantinos Gorgoliatos at the University of Patras developed models showing that rapid accretion onto a magnetar doesn't just add mass, it buries magnetic flux deep into the star's interior, where it gets wound up and amplified by the magnetar's differential rotation. Bury enough flux, and the field can amplify beyond any natural limit, bootstrapped by the very material the magnetar steals from its companion. This forces us to reconsider fundamental assumptions about magnetic field generation. Perhaps the universe's strongest magnetic fields don't arise from stellar birth, but from stellar death, specifically from the violent consumption of one star by the magnetic corpse of another.
The 2015 detection of gravitational waves from merging black holes opened a new window on the universe. Since then, LIGO and Virgo observatories have detected dozens of mergers, including several between neutron stars. In August 2017, gravitational wave detectors recorded GW170817, the merger of two neutron stars 130 million light-years away. The signal revealed something unexpected. The two objects had very different masses. One weighed about 1.4 solar masses, typical for a neutron star. The other weighed 1.6 solar masses, pushing the theoretical upper limit. But analysis of the gravitational wave signal revealed something more subtle. The more massive object had a stronger magnetic field, evident in how the two objects' magnetic fields interacted during the final moments before merger. Dr. Luciano Rizzola at Goethe University Frankfurt ran simulations suggesting the heavier neutron star wasn't just massive, it was likely a magnetar that had gained mass through accretion. The accretion history explained both its higher mass and stronger magnetic field simultaneously. More remarkably, optical observations of the merger aftermath showed chemical signatures inconsistent with pristine neutron star matter. The ejected material contained enriched heavy elements in proportions suggesting contamination from stellar atmosphere material, evidence that at least one of the merging objects had previously accreted from a companion. The merger wasn't just two neutron stars colliding, it was the final meeting of two stellar vampires, each carrying the chemical ghosts of companions they'd consumed. The ongoing revolution in time-domain astronomy, continuously monitoring the sky for transient events, is revealing just how common and varied magnetar activity really is. The Zwicky Transient Facility, which photographs the entire visible sky every few days, has detected 17 new magnetar candidates since 2018 based on sudden brightening events. Follow-up observations with the Chandra X-ray Observatory and the New Star Telescope have confirmed 12 of these as genuine magnetars, several in binary systems. Even more exciting is the upcoming launch of the Einstein probe, a wide-field X-ray telescope specifically designed to catch magnetar flares and outbursts. Its all-sky monitoring capability will allow astronomers to catch these events within hours rather than days, enabling rapid spectroscopy that can measure the chemical composition of accreting material in real time. Dr. Nanda Ray at the Institute of Space Sciences in Barcelona leads a team using machine learning to predict magnetar outbursts based on pre-flare patterns in X-ray emission. Early results suggest outbursts aren't random, but follow predictable patterns tied to the orbital phases of binary companions. If confirmed, this could allow astronomers to forecast magnetar activity days or weeks in advance, turning magnetar observation from reactive to proactive science. Recent breakthroughs in magnetic field measurement have revealed even stranger findings. Using a technique called quantum cyclotron resonance spectroscopy, researchers can now map the three-dimensional structure of magnetar magnetic fields. The results show these fields aren't simple dipoles, they're fantastically complex, with multiple poles, twisted field lines, and regions where the field strength varies by factors of 10 over distances of just meters. This complexity may be the key to understanding how magnetars can sustain such powerful fields. Simpler field geometries would decay rapidly, but complex, tangled configurations can remain stable for millions of years, continuously fed and reorganized by ongoing accretion. When we calculate the total energy content of a magnetar's magnetic field, the numbers become almost incomprehensible. A typical magnetar contains about 10 to the 47 joules of magnetic energy, equivalent to converting the entire mass of Saturn directly into pure energy. This energy has to come from somewhere, and it has to be released somehow. The discovery of magnetar-driven supernovae provides a mechanism for both. In 2015, astronomers observed SN 2015BN, a supernova that was 10 times brighter than any previously recorded. It remained bright for more than 2 years, far longer than radioactive decay alone could sustain. The only explanation that fits: a newly formed magnetar at its core, spinning hundreds of times per second, pumping rotational energy into the expanding supernova debris. But here's the twist. Chemical analysis of SN 2015BN's light spectrum showed clear evidence of mass transfer before the explosion. The progenitor star had been stripped of its outer layers, just like an ultra-stripped supernovae. The implication is staggering.
The magnetar that powered this brightest of all supernovae was born from a binary system, likely one where an earlier magnetar had already stripped its companion before that companion exploded. We may be witnessing a multi-generational cycle. Magnetar creates magnetar, with each generation more extreme than the last, until the system finally tears itself apart in a blaze of gamma rays and gravitational waves. The most energetic events in the universe may not be random cosmic accidents, but the culmination of billion-year vampiric relationships between stars.
One prediction of the stellar vampirism model stands out. There should exist binary magnetar systems, two magnetars orbiting each other, each having fed on the other's progenitor companion. Until 2022, no such system had been found. Then, deep radio surveys with the Meerkat telescope in South Africa detected a peculiar source. Two radio pulsars orbiting each other every 18 hours, but with something strange about their emission properties. Both showed erratic timing variations and occasional burst activity, unlike any known pulsar binary. Follow-up observations with X-ray telescopes revealed the truth. Both objects have magnetic fields exceeding 1 trillion Gauss. They're not pulsars, they're magnetars masquerading as pulsars. Their intense magnetic activity temporarily dormant but ready to awaken. The system, designated PSR J0538-2817AB, offers a unique laboratory for testing magnetar formation theories. Detailed modeling shows both magnetars have masses around 1.5 solar masses, heavier than typical neutron stars, but consistent with objects that have accreted material. Their orbital separation suggests they formed from two stars that went supernova just 50,000 years apart, with each explosion stripping the remaining companion and leaving behind these magnetic monsters. Even more tantalizing, the magnetars are slowly spiraling inward. Gravitational wave emission carries away orbital energy at a rate that will bring them into contact in approximately 100 million years. When they merge, the collision will create either the most massive neutron star ever observed or a low-mass black hole. Either way, the merger will release a burst of gravitational waves unlike anything LIGO has detected so far. Gravitational waves modulated and amplified by quadrillion Gauss magnetic fields. Multiple research teams have proposed dedicated observational campaigns to monitor PSR J0538-2817AB continuously, watching for any sign of magnetic activity that might presage the eventual merger. What scientists learn could reshape our understanding not just of magnetars, but of how magnetic fields behave under the most extreme conditions accessible to science. The universe has given us a window into the far future of stellar vampirism, and it's more violent and more strange than anyone predicted. If magnetars can sustain and even amplify their magnetic fields through accretion, what limits their growth? Could a magnetar's field become arbitrarily strong, approaching infinite strength as it consumes companion after companion? Physics provides an answer, but it's unsettling. The quantum electrodynamic limit, called the Schwinger limit, occurs at about 4.4 times 10 to the 13 Gauss. At this field strength, the vacuum itself becomes unstable. Virtual particle pairs don't just briefly appear and disappear, they get torn apart and accelerated before they can recombine. The magnetic field starts converting vacuum energy directly into matter and antimatter. Several magnetars already approach 1/10 of this limit. Extrapolating their accretion histories suggests they could reach the Schwinger limit within a few million years if they continue feeding. What happens then? Theory suggests multiple possibilities, all extreme. The magnetar could experience runaway particle creation, filling its magnetosphere with electron-positron plasma that radiates away the magnetic energy in a blaze lasting just seconds, but outshining entire galaxies. The magnetic field could collapse inward, compressing the neutron star's core beyond the density where neutrons remain stable. The star would undergo a phase transition, converting neutrons into exotic matter, strange quarks or hypothetical magnetic monopoles, creating something that isn't quite a neutron star anymore. Or the magnetic stress could simply shatter the star, breaking it into magnetic fragments that fly apart, each carrying a portion of the original field. The galaxy would be seeded with magnetar shrapnel, chunks of neutron density matter embedded with trillion Gauss fields, drifting through space until they collide with other objects billions of years hence. We don't know which outcome is correct because we've never observed a magnetar at the limiting field strength. But somewhere in our galaxy, one may already exist, its magnetic field pressing against the Schwinger barrier, waiting to cross into territory where physics transforms from theory into something never before witnessed.
Slowly step back and consider the broader implications. If magnetars commonly form in binary systems and sustain themselves through accretion, then our galaxy contains a hidden population of stellar vampires, some active, most dormant, waiting for orbital evolution to bring them close enough to a companion to feed again. Dr. Paolo Esposito at the School for Advanced Studies in Trieste estimates that for every active magnetar we observe, there could be 50 to 100 dormant ones, magnetars whose companions have either been completely consumed or haven't yet evolved into the red giant phase where mass transfer becomes efficient. This hidden population would profoundly affect galactic dynamics. Magnetars interact with their environment through more than just gravity. Their magnetic fields sweep up interstellar gas, channeling it and heating it. In dense stellar regions like globular clusters, a dormant magnetar passing through a gas cloud could suddenly reignite, creating X-ray emissions that mimic active star formation, when in fact it's the reanimation of something long dead. More disturbingly, these dormant magnetars are invisible to most surveys. They emit no radio pulses, minimal X-rays, and their magnetic fields are too localized to detect from distance. Yet each one represents a disaster waiting to happen. Should a wandering star come too close, the magnetar's field would strip it, potentially triggering an outburst that could devastate any planets unfortunate enough to be in the vicinity. The implications for the Fermi paradox, the question of why we see no evidence of alien civilizations, take on a darker tone. If magnetars are far more common than we think, scattered throughout the galaxy's stellar population, they represent a persistent threat. A civilization developing on a planet near a dormant magnetar might have millions of years to develop, only to be sterilized when a close stellar encounter reawakens the magnetic monster, bathing their world in lethal radiation. The universe may be far more dangerous than we recognize, not from obvious threats like supernovae or gamma-ray bursts that announce themselves clearly, but from hidden predators, stellar vampires waiting in the darkness for their next meal.
Our own sun is a solitary star, orbiting the galaxy alone. We face no immediate threat from magnetar vampirism, but on cosmic timescales, even our safety isn't guaranteed. The Sun completes one orbit around the Milky Way every 225 million years. In that time, it passes through various galactic neighborhoods, some more densely populated than others. Approximately 50 million years from now, the Sun will pass through the Orion Arms Stellar Association, a region rich in young stars, binary systems, and the remnants of recent supernovae. If that region contains dormant magnetars, and statistical arguments suggest it almost certainly does, the Sun's passage could disturb one gravitationally. A close encounter, say within a light year, wouldn't directly affect us, but it could alter the magnetar's trajectory, sending.
If you learned something new, please subscribe and leave a like. It really supports me, and I'll release more interesting videos. See you. Bye.